Thanks for David to share the experience on how to avoid overloading in distributed systems. As we know, user experience to a service is often determined by the longest latency. This is known as a tail at scale problem. So our next speaker, William Thurston, will share his experience in Netflix to optimize service tail behavior by self-tuning. Let's welcome William.
Hi everybody, I'm joining you today from my basement where my cats might also make an appearance. My name's William Thurston and I'm going to be talking about better resilience through self-tuning. It's something we've been doing at Netflix now for a while that helps make our developers both more productive and build more resilient services. And that really will be the focus of the technology that we talk about today is how we build resilient, safe, fast, and secure services at Netflix. So, of course, our thing, we've got to keep everybody streaming. With the impact of COVID, one of the reasons why I'm in my basement, not with you there in person, Netflix, of course, had a whole bunch of people join our service and stream a lot more content as a result of staying home and all of the impacts. And so with that scale came a lot of the technology that we've deployed over the years really flexing and doing its work. And we're going to take a look at one of those services today that makes the Netflix streaming experience work. If it wasn't running, you wouldn't be seeing trailers, you wouldn't be getting the movies and the shows that you love. And so we'll take a look at the end of this talk and see how that technology all gets put together to make that excellent experience that you're used to. And so the thing that we're focusing on, the problem really that we have to deal with is minding the tail. And when we talk about the tail, I'm talking about tail latencies and the requests maybe that take a little bit longer than expected, or just never complete for whatever reason. And that's where things go wrong for customers generally. We can see here from this quote, this is from Matt Klein. He's the creator of Envoy, which is a load balancing proxy that's very popular in the open source. He says, tail latency is most important because it's the hardest thing to reason about. Debugging throughput is easy, but P99.9 latency issues are very hard. And we're going to talk a little bit about why that is and some of the solutions that we've come up with. So this right here, this is what you think on the slide. This is what you think your customers are experiencing, somewhere in the middle of this latency distribution. What they're actually experiencing, though, is what we see on this one, which is out here on the tail. And that might be a little bit counterintuitive. Like, why is that the case? That's not how averages work. Well, the reason for it is because this is what your call graph looks like. I've redacted some names here, obviously, but this is a visualization of a single request in a Netflix and the huge fan out that it has and the hundreds of other services that it calls in order for you to do the things that you want to do when watching movies and shows on Netflix. Because of the number of calls here, we can see that even if something happens just 1 in 100 times, it's almost guaranteed to happen every time a request comes in. And so this is what I mean by minding the tail, paying attention to those things that are outliers in latency or success rates, and doing something to address it. We have to, or this would become a problem for people on Netflix. And so why is this hard? Well, one of the big reasons why it's hard is because there's just so many machines involved. There's at least 100 different machines involved in that call graph that you just saw. They all have sort of non-deterministic behavior in a lot of cases. And this can really sort of just devolve into what feels like randomness, especially as we're debugging our systems and trying to get a better understanding of what's happening, where things are going wrong, and how we can make a better customer experience. And so we're going to talk about a few different pieces of tech today. The first one of those is going to be concurrency limiters. You're probably pretty familiar with them. They sort of like just limit the amount of traffic that can come into your service. Sounds pretty basic, but there's actually a lot going on there. The next we're going to talk about are hedge requests. This helps us really just avoid the very slowest things in a distributed system when there's that many services and calls involved. Lastly, we're going to talk about load balancing, which on its own is a very complex topic. But we're gonna keep it simple, and I'll show you why that is here a little bit later. And then we're gonna pull it all back together and look at that Netflix service that has to be running for you to get the experience that you're used to, and show how these technologies pull that off. So first, we're talking about concurrency limits. And this is to make sure that your service just doesn't experience a huge amount of overload. We can see here a thundering herd of, in this case, buffalo. But this might be a retry storm coming at your service, ready to knock it over. We've probably all operated and run services where the amount of traffic showing up is just more than it can handle, and everything falls over. We don't go from serving most of our traffic well and turning a few requests away. Most services, when they have too much traffic or too much load, just simply stop working and everything begins to return errors. We're going to talk about how we avoid that situation at Netflix. And so there's a couple approaches that you can take and that we generally do as we're building our own services. I call this one the wild guess concurrency limit. It's generally pretty wrong. Sometimes it helps. Oftentimes I've actually seen it hurt just as often because maybe you've set that limit either far too low or far too high, where when it's necessary for this thing to be doing its job properly, it's just not. And it either leads to a degraded customer experience one direction or the other. The next one is what I call an artisanal concurrency limit. And this is one that's been handcrafted over time. You've probably done things like squeeze tests, maybe load tests of your system, and you're tweaking parameters just here and there to get the perfect limit. But then the next time you deploy a new version of your service, that value that you previously determined, it's decayed, right? The code has changed, the behavior has changed. And sometimes that behavior change may even come from the services you call rather than directly your own doing. And so this is something that takes a lot of time, but typically decays quite quickly and may not be a useful value over time. And so at Netflix, what we've done is we've developed adaptive concurrency limits. And these are constantly adapting to system behavior. We can see here on the graph that the discovered limit actually goes up and down over time. These are, peaks and valleys across multiple days. And one of the reasons why this can happen is traffic patterns change, right? The string localization may happen more in times where international users are more prominent on the service. There may be certain titles that become popular at certain times of day. All of these things mean that even if the code is unchanging, the workload of our systems is still changing. And so we do need something adaptive that discovers those limits and adjusts to what's happening. And so we can see here that if the discovered limit has this sort of a pattern and changes all throughout the day, there's essentially no number we could have load tested or squeeze tested or figured out with an artisanal concurrency limit that's correct. We'd either be too high or too low, or even if we did something like take the average, we're both too high and too low, depending on the time of day. So we see that a single number really just won't work. And then this here, you can see in the highlighted area of the graph, this is a system shock. This occurred as Netflix moved traffic amongst different regions around the world to avoid a failure in a local region. And as that new capacity came online to handle increased load in a new geographic location, the new servers were still, warming up. They are largely like Java virtual machines. And so they took a little bit of time to get going. And so the new servers that had joined had far lower concurrency limits than the existing servers that had been serving traffic for a while. And so we can see here the average limit actually dropped as those new machines came online before they warmed up and were able to get back to the standard limits. And so even here we can see that system shocks have a pretty big impact on what is actually possible to serve on any individual machine. And this is yet another reason why you need this sort of adaptive behavior. And so we're going to take a look now at a simulation, what it looks like with simulated traffic and where a service would typically fall over and just begin returning errors to clients. So in this case here, the first blue arrow that we see on the graph, these are just success. This is normal load coming into a service. everybody's happy, they're getting the responses they expect, and things are working great. At the next step, though, we see a lot of red, and these are actually throttled requests. This is the concurrency limiter, discovering a limit, kicking in, and turning away new traffic coming into the service. The very beginning of this red section is actually where most services would fall victim to that thundering herd and begin returning all errors. The service at this point is at 100% CPU and has discovered what is a safe amount of traffic to allow in and how much it needs to turn away. We can see here that the latencies actually stay flat as well. Even though we've reached that complete saturation point for these machines, the customers that are getting in are still receiving fast responses as they would in a normal operating scenario. One thing to notice here is that the amount of traffic coming in has now reached almost 5x the original amount, and we have almost 2 or 3 times the initial success still being returned as success, even though we've now saturated the service. As this continues on, we can see as more and more traffic shows up as we go to 10 or even 15 times the initial traffic amount, that the amount of success does lower down as it's spending so much time turning traffic away, but it never goes into that spiral where things just completely break and no requests are serviced at all. And all throughout here, the latency does stay flat, as we can see on these graphs. And so what we've seen here is that adaptive concurrency limiters are both safer and simpler. And that's important because we need developers, building new features, bringing new things to the service, not focused on constantly retuning and adjusting those limits. And so here we focused on simpler and safer. Next, we're going to focus on what we do with all the things that are slow. And so that leads us into hedge requests. Our services, of course, it'd be great if they either succeeded or failed quickly, but that's not generally the world that we live in. Oftentimes, requests are sent and we don't know if they're going to succeed or fail or when they might come back. And that's where hedge request comes in. It helps address sort of the long tail, right? It's the P99 and greater of those requests that cause customer impact and customer pain. And so what hedge requests allow us to do is to focus on the tail. This avoids and hides problems in the tail, and it allows us to take those slowest requests and essentially just avoid them. That's really the primary purpose. And we do that by focusing on what is the latency distribution of requests that are being sent from a client to a service, and at what level should we maybe assume, hey, that request might be one of those that just doesn't come back. And so we're constantly keeping track of what's like the P95 or P99 of any client request that is outbound. And when the current request that's being sent crosses one of those thresholds, we'll send another and just take back whatever is the first to arrive. And this really allows us to flatten the latency distribution pretty significantly and turn things that used to be timeouts or errors in this sort of a distributed system and turn them into completed, albeit a little bit slower responses. And so, failures, they do happen in the tail. That's pretty significant here. And we want to make sure that we don't wait for them. We don't want to wait for a failure. We need to go out and get a success while that first request is still in flight. And so we talked about limits and keeping things simple. We've now talked about making sure we don't wait for the slowest request in our system. And now we're going to talk about how we get around servers that are maybe troublesome overall and keep showing up as an issue. And that's going to come in with load balancing. Load balancing, in this case, it helps us avoid bad servers. And that's not just servers that are giving us errors or the wrong responses. It's also avoiding servers that are slower or maybe just not as performant for the responses that we need. And there's a ton of research in this space. There's all sorts of ways to do load balancing, to share information about what's the best server to call from our client. But at Netflix, we've actually decided to just keep it simple. We use what's called a choice of 2 load balancer. And what it does is it just picks 2 random servers and sends the request to whichever one has the fewest outstanding requests. This is about 95% as good as some of the more advanced algorithms out there that don't share state of all of the servers. And it allows us to focus, just more energy and more attention on the adaptive behaviors of the system. This helps us just avoid, those bad nodes that just do pop up from time to time. And so in this case, simple is actually near optimal. And so we put all three of these things together, and we're going to take a look now again at that Netflix service, the one that, every time you see a trailer or a preview or one of those movies or shows that you love watching, this needs to be working for you to succeed in watching anything on Netflix. And so here we're going to take a look at just a random minute in the day as this service operates. And we can see here, all of these numbers, these are rates. We have deadline exceeded, we have okay, and we have unavailable. And deadline exceeded is essentially just timeouts. Unavailable means that we couldn't get to that server at all, even after multiple tries. And an okay, that's what we want, right? That's Netflix succeeding here. And so in this particular minute, we had about 50,000 RPS, or about 3 million total requests. And so as we dive in to these rates and to these numbers, we'll see how these technologies help here. And so in this case, we did the math, we turned these rates into numbers, and out of that 3 million requests, about 125 of them were already timed out before the client tried to call the server. 5 more of them timed out while the client was waiting for the server. And as we said, 1 just never succeeded in making that call. But what's interesting here is these are largely Java services talking to other Java services. You might go, well, wait a second. Why were there 125 timeouts before a service called somewhere else? And there were only 5 waiting for a response. And the answer to that is largely due to garbage collection pauses and just the normal variance in our system runtimes. In this case, those clients were doing their own work in memory, processing things. And at the point where they made that external call, maybe there was a garbage collection pause on that machine for a bit. And when that call was finally initiated, the timeout had already been reached from the caller above them. And so the system knew, that those 125 requests, nobody's waiting for them anymore. And so, it just stopped processing work. Those 5 that timed out were the server or other aspects of the system having trouble. And, in this case, with the adaptive concurrency limiters, the hedge requests, and the choice of 2 load balancing, the clients are actually able to avoid backend servers that are themselves going through garbage collection pauses or other slowdowns, and only talk to the ones that respond successfully and quickly. And that's a pretty neat thing. We've actually turned a distributed system, client to server communication, into a more reliable model than it is actually within memory on a single machine. And of course, every layer of the Netflix service stack is doing this as well. So even though there were 125 timeouts here due to things like garbage collection pauses, the layer above in that call graph was implementing these same sorts of functionalities and avoiding those error responses as well through things like head requests and the adaptive concurrency limiters. What does this look like from a latency perspective? Well, this service, it doesn't do a lot, but it does important stuff, and it responds in about a millisecond at the median. Even at 3 nines, it's only up around 80 milliseconds or so. And so this shows, and this is all measured from the client, so this shows just how well those mechanisms that we've been talking about help even keep latencies down for the most extreme outlier requests and responses in the system. And, the kicker here at the end is that this is actually 5 nines of availability. If you were doing the math there in your head as I was speaking, this is 99.999% available, which, certainly meets our goal. That's fewer than 1 in 100,000 requests failing. And this is one of the ways that we keep, Netflix reliable, streaming, and keeping you happy as you watch the newest things coming out. Thanks for joining me in my basement today. I guess we missed the cats. Maybe next time.